Right now, as you sit there listening to this, roughly 100 trillion neutrinos are passing through your body every single second. They came from the core of the sun, traveling 93 million miles across space, and when they reached Earth, they didn't stop. They didn't slow down. They passed through the entire atmosphere, through the roof above your head, through your skin, your bones, your organs, and out the other side without touching a single atom inside you. And they didn't stop there either. They continued straight down through the ground beneath your feet, through miles of solid rock, through the molten iron core of our planet, and out the other side of the Earth as if the entire world simply wasn't there. Tonight, we're going to find out why. Before we go any further, if you find this kind of deep dive into the hidden side of physics fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Also, before we begin, we're now live on Spotify. The link's in the description if you'd like to listen to us wherever you are. Now, let's begin. Let's start with something you already know, but probably haven't thought about deeply enough. Matter. The stuff you're made of. The stuff the Earth is made of. The chair you're sitting in. The walls around you. The ground beneath your feet. The air filling your lungs right now. All of it is matter, and all of it feels solid. When you knock on a wooden table, it resists your hand. When you stand on concrete, the concrete holds your weight. When you press your palm flat against a wall, the wall pushes back. You trust this completely. You walk across a room without ever worrying you'll fall through the floor. You sit in a chair without questioning whether it will hold you. You pour water into a glass and expect the glass to contain it. The solidity of matter is one of the most basic facts of your existence. You don't even think about it. It's so obvious it seems like it doesn't need explaining. But here's the truth that changes everything. Matter is not solid. It is almost entirely empty space. And understanding just how empty matter really is turns out to be the first step toward understanding why neutrinos can pass straight through the Earth as if it simply doesn't exist. Let's zoom in, way in, past the scale of everyday objects, past the scale of grains of sand, past even the scale of individual cells and bacteria. Let's go down to the level of atoms. Everything around you, everything you've ever seen or touched, including you yourself, is made of atoms. An atom is the basic building block of all ordinary matter. Every element on the periodic table, hydrogen, carbon, oxygen, iron, gold, uranium, is defined by the structure of its atoms. And atoms are small, incredibly small. A single atom of hydrogen, the simplest and lightest element, has a diameter of roughly 1/10 of a meter. To put that into perspective, if you lined up 10 million hydrogen atoms in a row, side by side, the entire line would measure about 1 millimeter. That's about the thickness of a credit card. 10 million atoms just across a distance you can barely see with the naked eye. Now, you might think that because atoms are so tiny, they must be like miniature solid spheres packed tightly together inside matter. Tiny billiard balls squeezed against each other with no gaps between them. That's actually what scientists believed for a long time. But in 1911, a physicist named Ernest Rutherford performed one of the most important experiments in the history of science and shattered that assumption forever. Rutherford and his team fired tiny, fast-moving particles called alpha particles at an extremely thin sheet of gold foil. If atoms were solid balls packed tightly together, every alpha particle should have been stopped or deflected by the foil. but that's not what happened. The vast majority of particles passed straight through the gold as if the foil wasn't even there. That was shocking. A few particles were deflected at small angles, and a tiny fraction bounced back entirely, ricocheting almost straight back toward the source. Rutherford famously said it was as if you fired an artillery shell at a piece of tissue paper and the shell bounced back at you. What Rutherford discovered was that an atom is not a solid ball. It has a tiny, incredibly dense core called the nucleus, surrounded by a vast region of almost completely empty space where electrons orbit at great relative distances. The nucleus contains almost all of the atom's mass, more than 99.9% of it. Virtually everything that gives matter its weight is concentrated in that minuscule central point. But the nucleus is fantastically, almost absurdly small compared to the atom it sits inside. If you scaled an atom up so that the entire atom was the size of a major sports stadium, one of those enormous football stadiums that seats 80,000 people, the nucleus at the center of that atom would be about the size of a marble sitting on the 50-yard line. A marble in the middle of a stadium. And everything else, the seats, the concourses, the parking lot, the vast open space above the field, all of that represents the empty void inside the atom. There's nothing there except a few electrons. And electrons themselves are so unimaginably small that they occupy essentially no volume at all. Let me say that again because it matters. The nucleus is roughly 100,000 times smaller in diameter than the atom it belongs to. That's a factor of 100,000. The empty space inside an atom isn't a small gap. It's overwhelmingly dominant. The atom is almost all nothingness with a speck of dense matter at the center. This means that the table you knocked on, the floor you're standing on, the planet beneath your feet, every mountain, every ocean, every layer of rock and magma, all of it is almost entirely empty. If you could somehow remove all the empty space from all the atoms in the Earth, if you compressed everything so that the nuclei were packed directly against each other with no space between them, the entire Earth would collapse into a ball roughly the size of a large sports arena. All 6 sextillion metric tons of our planet crushed into something you could walk around in a few minutes. That's how empty matter really is. So here's the question that should be nagging at you. If matter is mostly empty space, why does anything feel solid at all? Why can't you walk through walls? Your hand is made of atoms that are mostly empty. The wall is made of atoms that are mostly empty. 2 clouds of mostly nothingness should pass right through each other without resistance. But they don't. When you push your hand against a wall, the wall pushes back with enough force to stop you completely. Something is creating a barrier. Something is filling all that empty space with an invisible shield that prevents atoms from passing through each other. That something is a force. And to understand which force, we need to talk about the 4 fundamental forces of nature. Because everything that happens in the universe, every interaction between every particle that has ever existed, is governed by just 4 forces. Only 4. Every explosion, every chemical reaction, every heartbeat, every star that shines, every planet that orbits, every atom that holds together, all of it comes down to 4 forces operating at different strengths and different ranges. And understanding these 4 forces is the key to understanding why neutrinos behave so differently from everything else. The first force is gravity. Gravity is the one you know best. It's the force that keeps your feet planted on the ground, the moon in orbit around the Earth, and the Earth in orbit around the sun. Gravity is the force that shapes the large-scale structure of the entire universe. It pulls galaxies together into clusters. It collapses clouds of gas into stars. It holds the solar system in its elegant orbital dance. Gravity seems powerful. It certainly feels powerful when you trip and hit the ground. But here's the secret about gravity. At the scale of individual particles, gravity is absurdly, almost comically weak. If you compared the gravitational pull between two protons to the electromagnetic pull between a proton and an electron, gravity would be roughly 10 to the 36th power times weaker. That's a 1 followed by 36 zeros. Gravity only seems strong in everyday life because it's cumulative and it has infinite range. Every atom in the Earth pulls on every atom in your body. Add up the gravitational pull of roughly 10 to the 50th power atoms in the planet, and the combined effect is enough to keep you stuck to the surface. But at the level of individual particles, gravity is so feeble that physicists essentially ignore it entirely. It doesn't matter. It plays no meaningful role in how particles interact with each other. And it plays no meaningful role in the story of the neutrino. The second force is electromagnetism. And this is the force that secretly runs your entire life. Electromagnetism is responsible for almost everything you see, feel, and experience. Light is electromagnetic radiation. The colors you see, the warmth of sunlight on your skin, the radio waves carrying signals to your phone, the X-rays at the doctor's office, all of these are different forms of electromagnetic waves. The chemical bonds holding molecules together, the bonds that give water its properties, the bonds that hold your DNA in its double helix, those are electromagnetic. The rigidity of steel, the flexibility of rubber, the transparency of glass, the hardness of diamond, all of these material properties arise from how electrons interact electromagnetically within those substances. And here's the key thing, the thing that matters most for our story tonight. The reason you can't walk through a wall, the reason your hand doesn't pass through the table, the reason anything feels solid at all is electromagnetism. When you push your hand against a surface, what's actually happening at the atomic level is that the electrons in the atoms of your hand are getting close to the electrons in the atoms of the surface. Electrons carry negative electric charge. Negative charges repel other negative charges. As the electron clouds of your atoms approach the electron clouds of the table's atoms, they push against each other with enormous electromagnetic force. That repulsion is what you experience as solidity. You're not actually touching the table in the sense that your atoms are making physical contact with the table's atoms. The atoms never touch. Their nuclei never get anywhere near each other. What you feel is the electromagnetic repulsion between electron clouds, a force field that prevents the atoms from overlapping. Everything you've ever touched in your life, every surface you've ever felt, every person you've ever hugged, you never actually made contact. Not really. You felt electromagnetic force pushing back against you. This is why matter feels solid even though it's almost entirely empty space. Electromagnetism fills that emptiness with influence. It creates a shield, a wall of repulsion that prevents anything carrying electric charge from passing through. It doesn't matter that there's almost nothing physically there. The force is there, and the force is what stops you. The third fundamental force is the strong nuclear force, sometimes just called the strong force. This is the force that holds atomic nuclei together. Remember how the nucleus contains protons and neutrons? Protons carry positive electric charge. Positive charges repel each other electromagnetically. So there's an enormous electromagnetic force trying to push all the protons in a nucleus apart. In a large nucleus like uranium, which contains 92 protons, the electromagnetic repulsion between all those positive charges is tremendous. So why doesn't every nucleus immediately explode? Because the strong force is stronger than electromagnetism. Much, much stronger. At the distances inside a nucleus, the strong force is roughly 100 times more powerful than the electromagnetic repulsion between protons. It is the most powerful force in nature, which is how it got its name. It grabs protons and neutrons and binds them together so tightly that splitting a nucleus requires extraordinary energy. That's what nuclear fission is. You're literally tearing apart something held together by the strongest force in the universe. But the strong force has a critical limitation that changes everything. It has an extraordinarily short range. The strong force only operates across distances of about 1 femtometer, which is 1 quadrillionth of a meter. That's roughly the diameter of a proton or neutron. Beyond that distance, the strong force falls off so steeply that it essentially ceases to exist. It doesn't reach across the atom. It doesn't extend beyond the nucleus. It's like having the most powerful grip in the world, but arms that are only a trillionth of a centimeter long. Within its range, nothing is stronger. Beyond its range, it's nothing. The strong force works through particles called gluons and acts on a property called color charge. Only quarks and gluons carry color charge. Protons and neutrons are made of quarks, so the strong force holds them together. But electrons don't carry color charge. Photons don't carry color charge. And critically for our story, neutrinos do not carry color charge. This means the strong force has absolutely no effect on neutrinos. It cannot grab them. It cannot deflect them. It cannot interact with them in any way. The strongest force in nature is completely powerless against a neutrino. Remember this. Now we come to the fourth and final fundamental force. The weak nuclear force, usually just called the weak force. And this is where the story of the neutrino truly begins. The weak force is strange. It behaves differently from the other 3 forces in several important ways. Gravity and electromagnetism both have infinite range. They grow weaker with distance, but they never truly reach zero. You can feel the gravitational influence of a galaxy billions of light years away, even if it's vanishingly faint. You can detect electromagnetic radiation from stars that emitted their light billions of years ago. These forces stretch across the cosmos. The strong force has a very short range, about 1 femtometer, but within that tiny distance, it's overwhelmingly powerful. It does its job with brutal efficiency. The weak force is different from all of them. It has an extremely short range, even shorter than the strong force. The weak force operates at distances of roughly 1,000th of a femtometer. Let that sink in. 1,000th of a femtometer. That's roughly 1,000 times smaller than the diameter of a proton. At distances larger than this, the weak force drops off so catastrophically fast that it essentially vanishes. 2 particles basically have to be sitting on top of each other, overlapping at subnuclear distances, for the weak force to have any chance of doing anything at all. And even when particles are within range, the weak force is genuinely weak. That's literally why it's called the weak force. At comparable distances, the weak force is about 1 million times weaker than the strong force. It's roughly 10,000 times weaker than electromagnetism. It is the second weakest force in nature, stronger only than gravity. But unlike gravity, it doesn't have infinite range to compensate. It's both feeble and short-ranged. This combination makes the weak force the most subtle, most elusive, and most difficult to observe of all four fundamental forces. Despite its weakness, the weak force plays a role that's essential to the existence of the universe. It's responsible for certain types of radioactive decay. It's the force that allows a neutron to transform into a proton, or a proton to transform into a neutron, processes that are fundamental to the nuclear reactions powering the sun. Without the weak force, the chain of fusion reactions at the sun's core could not proceed. Stars could not convert hydrogen into helium. The sun would not shine. The universe as we know it could not exist. The weak force, for all its feebleness, is absolutely necessary for everything. The weak force is carried by three particles: the W+ boson, the W- boson, and the Z boson. These particles are extremely heavy. The W bosons have a mass roughly 80 times that of a proton. The Z boson is about 97 times the mass of a proton. This enormous mass is actually the reason the weak force has such a pathetically short range. In quantum physics, forces are transmitted by the exchange of particles between the interacting objects. The heavier the particle being exchanged, the shorter the distance over which the exchange can happen. The photon, which carries the electromagnetic force, has zero mass, which is why electromagnetism reaches across the entire universe. The W and Z bosons are enormously heavy, which confines the weak force to those impossibly tiny distances. Now here's why all of this matters. Imagine a neutrino flying through space. This particular neutrino was born in the core of the sun, produced during a nuclear fusion reaction. It left the sun's core at nearly the speed of light and traveled 93 million miles across empty space. Now it reaches the Earth. It enters the atmosphere and plunges into the ground. It encounters matter, real matter, trillions upon trillions of atoms packed together as rock and iron and silicate minerals. What forces could possibly make it stop? Let's go through the list. Gravity. The neutrino has an almost vanishingly small mass, so small that for decades physicists thought it might have no mass at all. Gravitational effects at the particle level are negligible even for much heavier particles. For a neutrino, gravity is meaningless. It cannot slow it. It cannot deflect it. It cannot stop it. Electromagnetism? This is the force that makes everything feel solid. This is the force that stops your hand when you push on a table. This is the force that makes walls impenetrable and floors rigid. This is the force that governs nearly every interaction you've ever experienced in your entire life. And the neutrino is completely, totally immune to it. The reason is simple. The neutrino carries no electric charge. Zero. None. Electromagnetism only affects particles that carry electric charge. Electrons have negative charge, so electromagnetism governs their behavior completely. Protons have positive charge, so electromagnetism acts on them with full force. But the neutrino is electrically neutral. Electromagnetic fields wash over it without any effect whatsoever. The vast electron clouds surrounding every atom in the Earth, the very clouds that create the barrier of solidity that stops everything else, have absolutely no influence on a passing neutrino. The neutrino doesn't see them. It doesn't feel them. The electromagnetic shield that makes matter impenetrable to you, the barrier that defines your entire experience of the physical world, is completely invisible to a neutrino. It might as well not exist. This is a profound point and it deserves emphasis. Everything you have ever experienced as resistance, as solidity, as the tangible physical reality of the world around you is electromagnetic in nature. And neutrinos are entirely deaf to electromagnetism. The entire framework that makes matter impenetrable to you does not exist for a neutrino. The walls you cannot walk through, the ground that holds you up, the planet that keeps you from floating away, none of these things present any electromagnetic barrier to a neutrino. The strong force? It's the strongest force in nature. Could it possibly grab a passing neutrino? No. The strong force acts only on particles that carry color charge. Quarks carry color charge. Gluons carry color charge. Protons and neutrons, being made of quarks, respond to the strong force. But neutrinos carry no color charge, not a trace. The strong force cannot interact with neutrinos any more than electromagnetism can. The most powerful force in the universe is completely blind to them. That leaves only one option: the weak force. The weak force, operating at distances 1,000 times smaller than a proton, with a strength millions of times feebler than the strong force, is the only channel through which a neutrino can interact with the matter of the Earth. That's it. One force. The weakest and shortest ranged of the four. That is the only doorway through which a neutrino can communicate with the material universe. Now consider what the Earth looks like from a neutrino's perspective. Every atom is a vast emptiness with a tiny nucleus at the center. The electron clouds are invisible because the neutrino carries no charge. The strong force can't reach it. Only the weak force could matter, and the weak force requires the neutrino to pass within 1,000th of a femtometer of a nucleus for anything to happen at all. The target is unimaginably small, within an atom that is itself unimaginably small. And even if the neutrino does pass that close, the weak force is so feeble that an interaction is still unlikely. For a neutrino, the Earth is not a solid ball of rock and metal. It's a vast, ghostly fog of tiny, widely scattered targets, each target being a nucleus offering an interaction area so microscopically small that the probability of a hit is almost zero. The neutrino passes through one atom, through the next, through billions upon billions of atoms, through miles of solid rock, through the molten iron core, through the entire planet, and almost certainly it touches nothing. Every second, roughly 65 billion neutrinos from the Sun pass through every square centimeter of the Earth's surface, facing the Sun. That's about the area of your thumbnail. 65 billion through your thumbnail every second. The number passing through your entire body at any given moment is in the trillions. And virtually all of them pass through you and through the entire planet without interacting with a single atom. Not because the Earth is small. The Earth is 8,000 miles across. But because the only force available to the neutrino is so weak, and atoms are so empty, and the required interaction distance is so impossibly small, that 8,000 miles of solid planet presents almost no obstacle at all. The universe built walls to contain almost everything. Electromagnetism makes matter solid. The strong force locks nuclei together. Gravity anchors planets and stars. But the neutrino slips past every one of these barriers because it simply doesn't speak their language. The only voice it hears belongs to the weakest, most short-ranged force in all of nature. And that whisper, barely audible across distances 1,000 times smaller than a proton, is simply not enough to stop a particle that's racing through a planet made mostly of empty space. And this raises an extraordinary question. If neutrinos barely interact with anything, if they can fly through an entire planet untouched, how do we even know they exist? How did physicists discover a particle that refuses to be noticed? The answer takes us back nearly a century to a mystery that baffled the greatest minds in physics, a crisis so severe that one legendary physicist was willing to abandon one of the most sacred laws of nature, and a desperate prediction of a particle so ghostly that even the man who predicted it feared it might never be found. To understand how physicists found a particle that refuses to be noticed, we need to go back to a time when the atomic world was still being mapped for the first time. The late 1800s were an era of explosive discovery in physics. Scientists were peeling back layers of nature that had been hidden since the beginning of time. And in 1896, a French physicist named Becquerel stumbled onto something nobody expected. He discovered that certain materials, particularly uranium, emitted invisible rays all on their own without any external energy source. The material just sat there on a shelf, and it radiated. Nobody understood why. Soon after, Marie Curie and her husband Pierre Curie expanded on this work, isolating new radioactive elements like radium and polonium. They showed that radioactivity was a property of certain atoms themselves, not something caused by chemical reactions or external conditions. The atoms were doing something internally, releasing energy from deep within their own structure. This was profoundly strange. At the time, atoms were thought to be indivisible, indestructible, and eternal. The very word atom comes from the Greek atomos, meaning uncuttable. But here were atoms apparently breaking apart from the inside, throwing off pieces of themselves, transforming into different elements entirely. Nature, it turned out, had a hidden world of activity happening at scales far below anything the eye could see. As physicists studied radioactivity more carefully over the following decades, they identified 3 distinct types of radiation coming from unstable atoms. They named them alpha, beta, and gamma after the first 3 letters of the Greek alphabet. Alpha radiation turned out to be clusters of 2 protons and 2 neutrons, essentially the nuclei of helium atoms, being ejected from the decaying nucleus at high speed. Gamma radiation was high-energy electromagnetic radiation, similar to X-rays but even more energetic. These 2 types of radiation behaved in ways that made sense. They obeyed the laws of physics cleanly. Energy went in, energy came out, and the books balanced. But beta radiation was different. Beta radiation consisted of electrons being shot out of the nucleus at high speed. And something about beta decay was deeply, disturbingly wrong. Here was the problem. When an unstable nucleus undergoes alpha decay, the alpha particle always comes out with essentially the same energy. This makes perfect sense. The nucleus starts in a specific energy state. It decays to a lower energy state. The difference in energy goes into the alpha particle. Since the starting and ending states are fixed, the energy of the alpha particle is fixed. Every time, the same energy. Clean, predictable, and perfectly consistent with the law of conservation of energy, which states that energy can neither be created nor destroyed, only transferred from one form to another. Physicists expected beta decay to work the same way. A nucleus in a specific energy state should decay to a lower energy state, and the emitted electron should carry away a fixed amount of energy. Every electron from the same type of decay should have the same energy. But that's not what experiments showed. Not even close. When physicists carefully measured the energies of electrons emitted during beta decay, they found something alarming. The electrons didn't all have the same energy. Instead, they came out with a wide range of energies, forming a continuous spectrum. Some electrons carried nearly the maximum expected energy. Others carried barely any energy at all. Most fell somewhere in between. The energy of the emitted electron appeared to be random, varying from one decay event to the next, even when the exact same type of nucleus was decaying in the exact same way. This was a crisis. A genuine crisis. Because if the nucleus starts at a known energy and decays to a known lower energy, a fixed amount of energy must be released. If the electron carries only a fraction of that energy, where does the rest go? It wasn't showing up as heat. It wasn't showing up as light. It wasn't being carried away by any other detectable particle. The energy simply vanished. It went in, and less came out. The books didn't balance. In 1927, two physicists named Charles Ellis and William Worcester performed a meticulous experiment that settled the question once and for all. They used a calorimeter, a device designed to capture and measure every bit of energy released during a process, to measure the total energy output during beta decay. If the missing energy was somehow being released in some hidden form that individual detectors were missing, the calorimeter would catch it. A calorimeter captures everything: heat, light, kinetic energy, all of it. Nothing escapes. The result was devastating. The calorimeter confirmed that the average energy released per decay was only about 1/3 of the maximum. The rest of the energy was genuinely gone, not hidden, not escaping in some unseen form of radiation. Gone. Vanished from the observable universe as far as anyone could tell. The experiment was repeated, refined, and confirmed. There was no mistake. Energy was disappearing during beta decay. This result shook physics to its core. Conservation of energy is not a minor rule. It is one of the most fundamental laws of physics. It underlies everything. Every equation, every calculation, every prediction in physics depends on the assumption that energy is conserved. If energy could simply disappear, then the foundations of physics would crumble. Centuries of work, from Newton to Maxwell to Einstein, rested on the bedrock that energy cannot be created or destroyed. And now, at the subatomic level, that bedrock appeared to be cracking. The crisis was so severe that some of the greatest physicists alive considered abandoning conservation of energy entirely. Niels Bohr, one of the founding fathers of quantum mechanics and one of the most brilliant physicists of the 20th century, seriously proposed that perhaps conservation of energy simply didn't apply at the subatomic level. Maybe, Bohr suggested, energy conservation was only an approximation, a rule that worked well for large objects but broke down when you got small enough. This was a radical, almost heretical idea. It would have meant that the most fundamental bookkeeping rule of the universe had an exception. That nature cheated, but only when nobody was looking closely enough. And Bohr was no fringe figure. He was one of the most respected physicists on Earth. When Bohr spoke, people listened. And he was telling them that maybe energy conservation wasn't real. Not everyone was willing to go that far. One physicist in particular refused to give up on conservation of energy. And his refusal changed the course of physics forever. On December 4th, 1930, Wolfgang Pauli sat down and wrote a letter. It was addressed to a group of physicists attending a conference in Germany, and it began with one of the most famous openings in the history of science. Pauli addressed them as "Dear radioactive ladies and gentlemen." The tone was half serious, half desperate. He knew he was about to propose something outrageous, and he wanted to cushion the blow with humor. And then he proposed something extraordinary. Pauli suggested that during beta decay, the nucleus emits not one particle, but two. The electron that everyone could see and measure, and a second particle that nobody had ever detected. This invisible particle, Pauli proposed, carried no electric charge, which is why it didn't interact with electromagnetic fields and couldn't be detected by any instrument known at the time. It had an extremely small mass, possibly zero, and it carried away exactly the right amount of energy to balance the books. The reason the electron's energy varied from one decay to the next was that the available energy was being split between the electron and this invisible companion. Sometimes the electron got most of the energy. Sometimes the invisible particle got most of it. The split was different every time, but the total was always the same. Energy was conserved after all. Nothing had vanished. Part of it was simply being smuggled out of the experiment by a particle so ghostly that no detector could catch it. Pauli knew how strange this sounded. He acknowledged in his letter that he had done what he called a terrible thing. He had proposed a particle that could not be observed. In physics, proposing something undetectable is dangerously close to proposing something that doesn't exist. It feels like cheating, like inventing an invisible friend to explain why the cookies keep disappearing. But Pauli trusted conservation of energy more than he trusted the limitations of current technology. He believed the particle was real even if nobody could prove it yet, and he was willing to stake his reputation on it. At first, Pauli called his hypothetical particle the neutron because it was electrically neutral. But 2 years later, in 1932, James Chadwick discovered the actual neutron, the heavy neutral particle that sits alongside protons in the nucleus. This created a naming conflict. Two different particles couldn't both be called the neutron. Chadwick's particle was large and heavy and sat inside every atomic nucleus in the universe. Pauli's particle was vanishingly light and almost undetectable. They needed different names. This is where Enrico Fermi entered the story. Fermi was an Italian physicist of extraordinary talent, one of the greatest theoretical and experimental physicists of the 20th century. Fermi took Pauli's vague proposal and turned it into a rigorous mathematical theory. He worked out the detailed physics of how beta decay could produce this unseen particle. He calculated the expected energy spectrum. He described the force responsible for the interaction, and he gave the particle its permanent name. He called it the neutrino, which in Italian means the little neutral one. The neutron was the big neutral particle in the nucleus. The neutrino was its tiny, elusive cousin, a beautiful name for a particle that seemed determined to hide from the universe. Fermi's theory of beta decay, published in 1933 and 1934, was a masterpiece. It described a process in which a neutron inside the nucleus transforms into a proton. During this transformation, two particles are created and ejected, an electron and a neutrino. More precisely, it's an antineutrino, the antimatter counterpart of the neutrino, but the essential physics is the same for our purposes tonight. The electron and the antineutrino share the released energy between them. Sometimes the electron gets more, sometimes the antineutrino gets more, but the total energy is always exactly what it should be. Conservation of energy is rescued. The books balance perfectly, just as they always had. No energy was ever missing. It was just leaving the scene by an exit nobody knew existed. What made Fermi's theory especially remarkable was that it identified the force responsible for this transformation. The process didn't involve electromagnetism. It didn't involve the strong force. It involved a new kind of interaction, one that Fermi himself was among the first to describe mathematically. This interaction was the weak force. Fermi showed that beta decay was mediated by the weak nuclear force, the same force we discussed earlier, the force with the absurdly short range and the feeble strength. The weak force was the engine of beta decay, the mechanism that allowed neutrons to become protons and protons to become neutrons. And the neutrino was its signature product, born from the weak force, interacting only through the weak force, invisible to everything else. Fermi submitted his paper to the journal Nature, one of the most prestigious scientific publications in the world. Nature rejected it. The editor said the theory was too remote from physical reality to be of interest to readers. Think about that for a moment. One of the most important theoretical papers of the 20th century, describing a particle that would eventually win multiple Nobel Prizes, was rejected because it seemed too speculative. Fermi published it in Italian and German journals instead, where it was received far more warmly. History, as it so often does, proved the editors of Nature spectacularly wrong. Now let's pause and really examine what a neutrino actually is, because understanding its properties is the key to understanding why it behaves so differently from every other form of matter you've ever encountered. A neutrino is a fundamental particle. It is not made of anything smaller. Unlike protons and neutrons, which are composite particles built from quarks held together by gluons, a neutrino is elementary. It is a basic building block of nature, one of the irreducible ingredients of the universe. Specifically, a neutrino belongs to a family of particles called leptons. The electron is also a lepton, so there's a family resemblance. But the neutrino and the electron differ in one absolutely critical way. The electron carries electric charge. The neutrino does not. And this single difference changes everything. The electron is one of the most interactive particles in the universe. Because it carries negative electric charge, it feels the full power of the electromagnetic force. Electromagnetic fields can push it, pull it, accelerate it, deflect it, trap it, and manipulate it with exquisite precision. Every piece of electronic technology you've ever used, every computer, every phone, every light bulb, every motor, works by manipulating electrons through electromagnetic forces. The electron lives in a world dominated by electromagnetism. It cannot escape it. It cannot ignore it. It is bound to it completely. The neutrino carries zero electric charge. This means electromagnetism has absolutely no effect on it. Electric fields cannot push it. Magnetic fields cannot deflect it. The photon, which is the carrier of the electromagnetic force, is completely invisible to a neutrino. A neutrino could fly through the most powerful electromagnetic field ever created. A field strong enough to rip atoms apart. And it would pass through without the slightest deviation. Not because it's tough or resilient, but because it simply doesn't participate in that interaction. Electromagnetism and the neutrino exist in the same universe, but speak entirely different languages. They cannot communicate. Think about what this means for a neutrino passing through matter. Everything you experience as solid, every wall, every floor, every planet, is held together and made impenetrable by electromagnetic forces. The solidity of matter, the resistance you feel when you push against a surface, is electromagnetic repulsion between electron clouds. But the neutrino carries no charge. It does not interact with electron clouds. It flies straight through them as if they were completely transparent. And to the neutrino, they are transparent. Every electron cloud in every atom is invisible, non-existent, as irrelevant as a painted wall is to a radio signal passing through it. Now consider the second missing property, color charge. This is the property that determines whether a particle feels the strong nuclear force. Quarks carry color charge, which is why the strong force binds them together inside protons and neutrons. Gluons also carry color charge, which is how they mediate the strong force between quarks. But neutrinos carry no color charge whatsoever, not a trace. The strong force, the most powerful interaction in all of physics, cannot touch a neutrino. A neutrino could fly directly through the center of an atomic nucleus, through the densest concentration of matter that exists in ordinary atoms, and the strong force would not exert even the faintest pull on it. The strongest force in the universe is completely blind to the neutrino. It might as well not exist. Then there's mass. For decades after Pauli proposed the neutrino, physicists debated whether it had any mass at all. Many assumed it was completely massless, like the photon. We now know that neutrinos do have mass, but it's almost incomprehensibly small. The exact value hasn't been pinned down yet, but the best measurements and calculations suggest that the mass of a neutrino is less than 1/1,000,000th the mass of an electron. And the electron itself is already tiny, with less than 1/1800th the mass of a proton. So a neutrino's mass is less than roughly 1/1000,000th the mass of a proton. This is so light that for most practical purposes, the neutrino behaves as if it were almost massless. Neutrinos travel at speeds so close to the speed of light that the difference is negligible for nearly any purpose. Why does the nearly non-existent mass matter? Because mass determines how strongly a particle responds to gravity. Gravity is already absurdly weak at the particle level. For a particle with almost no mass, gravitational effects are so vanishingly small that they are completely unmeasurable in any practical situation. No gravitational field produced by ordinary matter can meaningfully deflect a neutrino. Gravity is simply irrelevant to the neutrino's journey through the world. So let's tally up the score. The neutrino has no electric charge, so electromagnetism cannot touch it. The neutrino has no color charge, so the strong force cannot grab it. The neutrino has almost no mass, so gravity cannot influence it. 3 of the 4 fundamental forces of nature have essentially no effect on the neutrino. That leaves the weak force, only the weak force, the force that operates at distances 1,000 times smaller than a proton, the force that is millions of times weaker than the strong interaction, the force whose carrier particles are so massive that they confine its influence to an almost impossibly tiny volume of space. This single force, the weakest and most restricted of them all, is the only channel through which a neutrino can interact with any other particle in the universe. This makes the neutrino one of the most isolated objects in all of existence. Almost every other particle you can name interacts through multiple forces. A proton responds to all 4 fundamental forces. An electron responds to electromagnetism, gravity, and the weak force. Even a neutron, despite being electrically neutral, responds to the strong force, gravity, and the weak force. The neutron can be captured, deflected, absorbed. It participates in the material world through several channels. But the neutrino has stripped away everything except the weakest and most limited channel available. It has almost no way to communicate with the rest of the material universe. It exists alongside everything, yet is barely connected to anything. Now, the prediction of the neutrino was elegant, and the theory was beautiful. But physics demands evidence. You cannot accept a particle's existence based on theory alone, no matter how well the mathematics works. Someone had to actually catch a neutrino in the act of interacting with matter. Someone had to prove it was real. The problem was staggering. How do you detect a particle that barely interacts with anything? A particle that could fly through the entire Earth without touching a single atom. Every detector is made of matter. Every instrument relies on particles interacting with the detector's material, depositing energy, creating signals that electronics can record. But neutrinos don't do that. They fly through detectors the same way they fly through planets. Trying to catch a neutrino with a physics detector is like trying to catch a specific raindrop by holding out a thimble during a hurricane. Except the rain passes through the thimble without even getting it wet. The challenge consumed physicists for a quarter of a century. From Pauli's prediction in 1930 to the mid-1950s, no one could figure out how to catch a neutrino. Many physicists suspected it might be permanently undetectable, a necessary ghost that balanced the equations but could never be seen directly. Pauli himself reportedly bet a case of champagne that nobody would ever detect one. The particle he had proposed out of theoretical necessity might, he feared, forever remain a mathematical shadow with no physical confirmation. He lost that bet. In 1956, two American physicists named Frederick Reines and Clyde Cowan accomplished what many thought was impossible. They detected neutrinos. Their experiment, sometimes called Project Poltergeist, a fitting name for a ghost hunt, was brilliantly designed. They realized that while any single neutrino almost never interacts with matter, if you have enough neutrinos passing through enough target material, the sheer weight of numbers means a tiny handful will interact purely by chance. You don't need to catch every neutrino. You just need to catch a few out of trillions. And to get trillions, you need an enormous source. Reines and Cowan set up their experiment next to a nuclear reactor at the Savannah River plant in South Carolina. Nuclear reactors produce staggering numbers of antineutrinos as a byproduct of the fission reactions in their fuel rods. Roughly 50 trillion antineutrinos per second streamed through every square centimeter near the reactor core. By placing a large tank of target material in this intense flood and waiting patiently, they could hope to catch the rare antineutrino that happened to interact with something in the tank. Their detector used a clever method based on a specific signature. When an antineutrino interacts with a proton in the target material through the weak force, it can transform the proton into a neutron and a positron. The positron is the antimatter counterpart of the electron. It immediately collides with a nearby electron, and the two annihilate each other, converting their combined mass into a pair of gamma rays. These gamma rays are detectable. Then, a tiny fraction of a microsecond later, the newly created neutron is captured by a nucleus in the surrounding material, producing another distinct burst of gamma rays. The signature of a neutrino interaction is therefore two flashes of gamma rays separated by a specific, predictable delay. This double flash is distinctive. It is very difficult to mimic with background noise or other stray processors. If you see that precise pattern, two flashes with exactly the right energy and exactly the right time gap, you've almost certainly caught a neutrino. Reines and Cowan saw the signal. faint, rare, buried in background noise, but unmistakably there. They detected roughly 3 neutrino interactions per hour out of the trillions upon trillions of antineutrinos streaming through their detector every second. 3 per hour. The rest, the overwhelming, unfathomable majority, passed straight through without a trace. But 3 per hour was enough. 3 per hour was proof. The neutrino was real. It existed. Pauli's desperate gamble had paid off. Conservation of energy was safe. They sent a telegram to Pauli informing him that his particle had been found. Pauli, by all accounts, was delighted. He reportedly drank the case of champagne himself. Frederick Reines would eventually receive the Nobel Prize in Physics in 1995 for this discovery, 39 years after the experiment was performed. Clyde Cowan had died by then and could not share the honour, but the achievement belonged to both of them. The confirmation of the neutrino's existence was one of the great triumphs of 20th century physics. It validated conservation of energy at the subatomic level. It proved that theoretical predictions, even ones that seemed almost impossibly difficult to verify, could eventually be confirmed through ingenious experimental design. And it revealed that the universe contains a type of matter fundamentally different from anything humans had ever encountered before. A type of matter that is barely connected to the material world. A type of matter that can exist in unimaginable abundance all around us, passing through us at every moment, and yet remain almost perfectly invisible. Because here is what the discovery of the neutrino truly showed us. The universe is filled with a class of particle that is almost completely disconnected from the material world we experience. A particle that carries no electric charge, no color charge, and almost no mass. A particle that responds to only one of the 4 fundamental forces of nature, and that one force is the weakest and most short-ranged of them all. A particle so reluctant to interact that trillions can pass through an entire planet every second without a single one being stopped. And yet this particle is not rare. It is not some obscure curiosity found only in extreme conditions. Neutrinos are among the most abundant particles in the entire universe. Every cubic centimeter of space, including the space you're sitting in right now, contains roughly 330 neutrinos left over from the Big Bang alone. These are ancient, primordial neutrinos that have been drifting through the cosmos since the universe was about 1 second old. Add in the neutrinos being produced right now by the sun, by nuclear reactors, by cosmic ray interactions in the atmosphere, by supernova explosions across the cosmos, by the radioactive decay of elements deep inside the Earth itself, and the universe is absolutely swimming in neutrinos. They are everywhere. They are among the most numerous particles in existence, and they are almost completely invisible. The neutrino is the universe's greatest ghost. It was born alongside everything else, travels through everything else, and yet barely connects to anything. It was predicted out of desperation, named with affection, detected through extraordinary ingenuity, and continues to challenge our understanding of how matter interacts with matter. And the reason for all of it, the reason for its ghostly nature, its invisibility, its ability to pass through planets and stars as if they were made of nothing, comes down to the properties we've just described. No electric charge, no color charge, almost no mass. The only force available to it is the weak force. And as we're about to discover, the weak force makes the entire Earth, all 8,000 miles of rock, metal, and magma, look like almost nothing at all. Now we reach the heart of it. The central question: We know the neutrino has no electric charge, no color charge, and almost no mass. We know it interacts only through the weak force, the most feeble and short-ranged of the four fundamental interactions. But knowing these facts in isolation doesn't quite explain why the Earth is transparent. After all, the Earth is enormous. It is 8,000 miles of solid, dense matter, rock, iron, nickel, silicates, compressed under tremendous pressure. The planet contains roughly 10 to the 50th power atoms, an almost incomprehensible number of potential targets. Surely, in all that material, a neutrino should eventually hit something. The answer is almost always no, and understanding why requires us to think about what an interaction really means at the subatomic level. We need to understand a concept physicists call the interaction cross-section. This idea sounds technical, but it's actually beautifully intuitive once you see it clearly. And it's the key to understanding why a neutrino can fly through an entire planet without being stopped. Imagine you're standing on the edge of a vast, empty football field. Somewhere on that field, a single coin is lying flat on the grass. A penny. You can't see it because the field is enormous and the penny is tiny. Now, imagine you're blindfolded, standing at one end of the field, and you roll a marble across the grass in a random direction. What are the chances the marble hits the penny? Almost zero. The field is huge. The penny is tiny. The marble will almost certainly roll across the entire length of the field without ever coming close to the coin. This is obvious and intuitive. The probability of a hit depends on the size of the target compared to the total area the marble might cross. If the target is small relative to the space it sits in, most paths will miss it completely. Now, imagine the same field, but instead of one penny, there are 1,000 pennies scattered randomly across the grass. Your chances of hitting one are better, but still very small. 1,000 pennies on a football field still leaves most of the field empty. The pennies cover only a tiny fraction of the total area. You could roll 100 marbles and probably miss every single penny. This is essentially what a neutrino faces when it enters the Earth. The atoms of the Earth are like pennies scattered across a field, except the field is unimaginably vast compared to the pennies. And the relevant part of each atom, the part the neutrino can actually interact with, is far, far smaller than you might think. Here's why. Remember that an atom is mostly empty space. The nucleus sits at the center, roughly 100,000 times smaller in diameter than the atom itself. The electron cloud surrounding the nucleus is irrelevant to the neutrino because the neutrino carries no electric charge. It flies right through electrons as if they aren't there. So the only part of the atom that matters is the nucleus, but even the nucleus isn't really the target. Not the whole nucleus. The weak force doesn't operate across the entire nucleus. It operates at distances roughly 1,000 times smaller than the nucleus itself. This means the effective target isn't the size of the nucleus. It's 1,000 times smaller than that. It's a volume of space so tiny that it makes the already minuscule nucleus look enormous by comparison. Let me try to put this in perspective. If the atom were the size of a football stadium, the nucleus would be a marble at center field. That's the comparison we used earlier. Now consider the weak force target within that nucleus. If the nucleus is a marble, the region where the weak force can actually operate, the zone where a neutrino would need to be for the weak force to have any chance of causing an interaction, would be 1/1,000,000th of the diameter of that marble. It would be smaller than the wavelength of visible light. You couldn't see it even with the most powerful optical microscope on Earth. It would be a point within a point, a target so small that hitting it requires a coincidence so improbable it borders on miraculous. Physicists quantify this using the interaction cross-section. The cross-section is essentially the effective target area that a particle presents to an incoming projectile. It's measured in units of area, like square centimeters, but at subatomic scales, these areas are fantastically small. For electromagnetic interactions, the cross-sections are relatively large by particle physics standards, because electromagnetism has infinite range and strong coupling. A photon interacting with an atom has a cross-section on the order of 10 to the negative 24 square centimeters. That's already absurdly tiny, but it's large enough that photons interact with matter readily. Light doesn't pass through walls, X-rays don't pass through LED shielding. Electromagnetic interactions are common because their cross-sections, while small in absolute terms, are large enough that the density of matter ensures frequent hits. For the strong force, cross-sections are even larger at short range. Nuclear reactions happen efficiently when particles get close enough because the strong force is enormously powerful within its tiny domain. Neutrons, which carry no charge but do respond to the strong force, interact with nuclear quite readily. A free neutron passing through matter will typically be absorbed or deflected within a relatively short distance, sometimes just centimeters of material, because the strong force cross-section is large enough to make collisions frequent. But the weak force cross-section for a neutrino is in an entirely different universe. A typical neutrino from the Sun, carrying an energy of a few 100,000 electron volts, has a cross-section of roughly 10 to the negative 44 square centimeters. Let me help you understand how small that is. That number, 10 to the negative 44, means you write a decimal point followed by 43 zeros and then a 1. It is roughly 100 quintillion times smaller than the cross-section for an electromagnetic interaction. 100 quintillion, that's a 1 followed by 20 zeros. To put it another way, the effective target area that a neutrino sees when it approaches a proton or neutron through the weak force is 20 orders of magnitude smaller than the target area an electromagnetic particle would see interacting with the same atom. 20 orders of magnitude is not a small difference. It's the difference between a grain of sand and the entire planet Earth. The neutrino's target is not just small, it is incomprehensibly, catastrophically small compared to the targets available to almost any other particle. And this is the entire explanation. This is why neutrinos pass through matter. The cross-section is so minuscule that even in a material as dense and as deep as the entire Earth, the probability of a neutrino encountering a target close enough to interact with is negligible. Let me walk through this more carefully, because the numbers deserve to be understood. The probability that a neutrino interacts as it passes through a slab of material depends on three things. First, the cross-section, which is the effective target size. Second, the number density of targets, meaning how many nuclei are packed into each cubic centimeter of material. And third, the distance the neutrino travels through the material. You multiply these three numbers together, and the result tells you the probability of an interaction. The Earth's core is made primarily of iron and nickel, dense metals compressed under enormous pressure. The density at the center of the Earth is roughly 13 grams per cubic centimeter. This gives a number density of targets, the number of target particles in each cubic centimeter, of roughly 5 times 10 to the 24. That's a lot of targets 5 trillion particles packed into every cubic centimeter of material at the Earth's core. And the Earth is thick, about 12,742 kilometers from one side to the other through the center. That's roughly 1.3 times 10 to the 9th centimeters of material. So let's do the calculation. You take the cross-section of about 10 to the negative 44 square centimeters and multiply by the number density of about 5 times 10 to the 24 targets per cubic centimeter and multiply by the path length of about 1.3 times 10 to the 9th centimeters. The result is roughly 6.5 times 10 to the negative 11. That's 0.0000000000065. In other words, for any individual neutrino passing through the entire Earth from one side to the other through the densest core material, the probability of interacting with even a single nucleus is roughly 1 in 10 billion. 1 in 10 billion. The neutrino has a 1 in 10 billion chance of interacting as it crosses the full diameter of the Earth. That means roughly 10 billion neutrinos would need to pass through the Earth for just one of them to interact. And remember, about 65 billion solar neutrinos pass through every square centimeter of the Earth's surface, every single second. So in every second, out of those 65 billion neutrinos crossing your thumbnail, only a handful interact anywhere in the entire volume of the planet. The rest, the overwhelming, staggering majority, pass through all 8,000 miles of rock and iron and emerge from the other side completely untouched. The Earth, from a neutrino's perspective, is essentially transparent. It is not a solid barrier. It is not even a thin veil. It is almost nothing. The neutrino barely notices it. And this is not a marginal result. The neutrino doesn't almost interact. It doesn't come close to interacting and just barely miss. The probability is so fantastically low that the Earth might as well not be there. If you doubled the Earth's diameter, the probability would double, but doubling a 1 in 10 billion chance still gives you a 1 in 5 billion chance. Still effectively zero. If you stacked 10 Earths in a row, front to back, the probability would increase tenfold, but it would still be only about 1 in a billion. You would need to stack roughly 10 billion Earths in a row to give a single neutrino a reasonable chance of being stopped. This is where the famous LED wall comparison comes in, and it's one of the most striking illustrations in all of physics. Physicists have calculated that even a single neutrino could fly through a solid wall of lead-1 light-year thick and still have roughly a 50-50 chance of emerging from the other side without interacting with a single atom. 1 light-year of solid LED. Think about what that means. A light year is the distance light travels in 1 year, about 9.46 trillion kilometers. That's an almost incomprehensible distance. The nearest star to our Sun, Proxima Centauri, is about 4.24 light years away. A wall of solid lead stretching from here to nearly a quarter of the way to the nearest star. Not a thin sheet, not a few meters, not a few kilometers, a light year. Roughly 9.5 trillion kilometers of solid, dense metal. Lead is one of the densest common materials available, about 11.3 grams per cubic centimeter. It's the material we use specifically because it's good at stopping things. We put LED shielding around X-ray machines because LED is excellent at absorbing radiation. We use lead to shield nuclear reactors. Lead stops electromagnetic radiation, it stops beta particles, it significantly attenuates gamma rays. and a light year of it wouldn't reliably stop a neutrino. The neutrino would have roughly even odds of sailing straight through. That's how weak the weak force interaction really is. The cross-section is so unimaginably small, and the required proximity so impossibly close, that even packing matter as densely as possible for a distance that dwarfs the imagination still doesn't guarantee a collision. This comparison is not an exaggeration. It's not a metaphor or an approximation used for dramatic effect. It's a straightforward calculation based on the measured cross-section of neutrino interactions and the known density of LED. Physicists routinely use it because nothing else adequately communicates just how weakly neutrinos interact with matter. No everyday analogy works. The numbers are simply too extreme for ordinary comparisons to capture. Now, I want to make something very clear because it's a point that trips people up. The neutrino is not somehow immaterial. It's not a ghost in the mystical sense. It's not passing through some other dimension. It doesn't have any special ability to phase through solid objects like a science fiction hologram. The neutrino is a real, physical particle moving through real, physical space. It has energy. It has momentum. It has mass, even if that mass is incredibly small. It exists in the same universe as everything else, occupies the same space, follows the same laws of physics. The reason it passes through matter is not because it's doing something strange, it's because matter itself, at the atomic level, is almost entirely empty space, and the only force that could cause the neutrino to interact with the tiny specks of matter that do exist in the emptiness is the weakest, shortest ranged force in nature. The neutrino isn't avoiding matter. It's flying through the enormous gaps between nuclei, blind to the electron clouds that fill those gaps, with the only possible interaction mechanism requiring it to pass within 1,000th of a femtometer of a nucleus. And the odds of that happening purely by random chance as it flies through are vanishingly small. It's like firing a bullet through a room full of widely spaced hula hoops. The bullet isn't phasing through the hoops, it's flying through the gaps between them. And if the hoops were 1 billion times smaller and the room were 1 trillion times bigger, you'd have something approaching the situation a neutrino faces inside the Earth. There's another important subtlety that makes the situation even more extreme. The cross-section for neutrino interactions isn't fixed. It depends on the energy of the neutrino. Higher energy neutrinos have slightly larger cross-sections, meaning they're slightly more likely to interact. Lower energy neutrinos have even smaller cross-sections. The neutrinos produced by the Sun, which are the most common neutrinos passing through the Earth, have relatively low energies by particle physics standards, typically in the range of a few 100,000 to roughly 15 million electron volts. At these energies, the cross-sections are at their most minuscule. These solar neutrinos are the most ghostly of all, interacting even less readily than higher energy neutrinos produced by cosmic ray collisions or supernova explosions. At much higher energies, cross-sections grow. A neutrino with an energy of 1 trillion electron volts has a cross-section roughly 1 billion times larger than a typical solar neutrino. That sounds like a huge gain until you remember that 1 billion times 10 to the negative 44 is still only 10 to the negative 35. Still fantastically small. Even these high-energy neutrinos can pass through the Earth with only a modest probability of interacting. It takes truly extreme energies, far higher than what the Sun produces, before the Earth begins to become even slightly opaque to neutrinos. At energies around 10 to the 15 electron volts, roughly 1,000 trillion electron volts, the cross-section grows large enough that the Earth starts to absorb a meaningful fraction of neutrinos passing through it. But such energies are extraordinarily rare in nature, produced only by the most violent astrophysical events. For the overwhelming majority of neutrinos in the universe, the Earth is transparent. Not partially transparent, not mostly transparent, almost perfectly transparent. The planet blocks roughly 1 in 10 billion of the solar neutrinos that enter it. It lets 99.999999% of them through completely untouched. If you could somehow see the world through neutrino vision, the Earth would be almost invisible. A faint haze, barely perceptible, like looking at a single sheet of the thinnest tissue paper from a mile away. Let me give you one more comparison to drive this home, because the scale is so extreme that repetition actually helps. Think about visible light and glass. Glass is transparent to visible light. Photons pass through a window pane because the electromagnetic properties of the glass are such that visible wavelengths aren't absorbed or scattered efficiently. But this transparency has limits. Stack enough glass together, hundreds of meters of it, and eventually it becomes opaque. Light gets absorbed. The material wins eventually. The transparency of glass to light is real, but finite. Now consider the neutrino and the Earth. The Earth is far denser than glass. It's thousands of miles thick. And the neutrino passes through it more easily than light, passes through a single pane of glass. The transparency of the Earth to neutrinos is so extreme that to find a comparable opacity, to find enough material to actually block neutrinos the way a wall blocks light, you'd need to compress the material into a barrier a light year thick. The Earth to a neutrino is millions of times more transparent than the clearest glass is to light. It's more transparent than air is to light. It's more transparent than the vacuum of outer space is to light, because even the vacuum of space has dust particles that eventually scatter photons over long enough distances. The Earth is more transparent to neutrinos than almost any material is to any other form of radiation. This is why physicists sometimes describe neutrinos as barely being part of the material universe. They exist in it. They travel through it. They carry energy and momentum through it. But they interact with it so rarely that for practical purposes, the material universe is almost invisible to them. They are particles that exist in a kind of profound isolation, surrounded by matter at all times, yet almost never connecting with it. And here is something remarkable that emerges from all of this. The transparency of the Earth to neutrinos tells us something deep about the nature of matter itself. It reveals that what we think of as solid, as substantial, as real in the tangible sense, is mostly a product of one specific force: electromagnetism. Take away electromagnetism, or rather take away a particle's ability to feel electromagnetism, and matter stops being solid. It stops being a barrier. It stops being anything at all. The solidity of the world is not an intrinsic property of matter. It's a consequence of the electromagnetic interactions between charged particles. For any entity that doesn't participate in those interactions, the world is made of almost nothing. The neutrino shows us a radically different perspective on physical reality. To us, the Earth is an 8,000-mile ball of solid rock and metal. It is massive, dense, and impenetrable. We build our lives on the assumption that the ground beneath our feet is solid and reliable. We trust that matter is substantial. But to the neutrino, all of that substance is an illusion created by a force it cannot feel. The neutrino sees a universe that is almost entirely empty. punctuated by targets so small and interactions so rare that the vast majority of matter might as well not exist. Both perspectives are correct. The Earth is solid for us because we are made of charged particles that interact electromagnetically. The Earth is transparent for neutrinos because they are not. There is no contradiction. The same physical object can be an impenetrable wall or an invisible wisp, depending on what forces you have access to. This is one of the most profound lessons in all of physics. Reality is not one thing. It depends on how you interact with it. And this brings us to a paradox that has driven some of the most important physics experiments of the past 70 years. If neutrinos almost never interact with matter, if the Earth itself is barely an obstacle, how could anyone ever hope to detect one? How do you catch a particle that can fly through a light year of LED? The answer, it turns out, lies in the one word hidden in all these statistics that we've been glossing over. Almost. Neutrinos almost never interact. Almost all of them pass through the Earth untouched. The cross-section is almost zero. But almost is not the same as never. And the difference between almost never and absolutely never turns out to be one of the most important distinctions in the history of science. Because if you watch enough neutrinos for long enough, with a big enough detector, buried deep enough underground to block out everything else, eventually, inevitably, one of them will stop. One of them will interact. One ghost, out of the trillions streaming through every second, will finally bump into a nucleus, trigger the weak force, and leave behind a signal that human ingenuity can detect. And what that signal reveals about the universe is nothing short of extraordinary. The difference between almost never and absolutely never is everything. If neutrinos truly never interacted with matter, they would be undetectable in principle. They would be mathematical phantoms, necessary for equations to balance, but forever beyond the reach of experiment. Physics would have to accept their existence on faith. And physicists are deeply uncomfortable doing that. But neutrinos don't never interact. They almost never interact. And almost is a crack in the door, a tiny opening that human ingenuity has learned to exploit with astonishing results. The strategy is elegant in its simplicity, even if the execution is monumentally difficult. You cannot make a neutrino interact more often. The cross-section is fixed by the laws of physics. The weak force is what it is. You cannot strengthen it or extend its range. So instead, you play the odds. You flood your detector with as many neutrinos as possible. You fill it with as much target material as possible. You wait as long as possible. And you rely on the sheer weight of numbers to force a few interactions to happen purely by statistical chance. Think of it this way. If you flip a coin and need it to land perfectly on its edge, the probability for any single flip is incredibly small, perhaps 1 in several thousand. But if you flip that coin 1 billion times, you will almost certainly see it land on its edge at least once. Not because any individual flip is likely to produce that outcome, but because you have given probability enough opportunities to work. Neutrino detection operates on exactly the same principle. Any single neutrino passing through your detector has an almost zero chance of interacting. But if trillions stream through every second, and you wait for hours or days or months, the mathematics of probability guarantees that a handful will interact. A tiny, precious handful. The challenge is recognizing those rare interactions when they occur. Because while trillions of neutrinos are passing through your detector, so are cosmic rays, natural radioactivity from the surrounding rock, stray particles from the atmosphere, and 1,000 other sources of noise. Detecting a neutrino interaction is like trying to hear a single whisper in a stadium full of screaming fans. The whisper is real. It's there, but it is buried under an avalanche of competing signals that threaten to drown it out completely. This is why neutrino detectors are built deep underground. By placing the detector hundreds or even thousands of meters below the Earth's surface, you use the rock above as a natural shield. Cosmic rays, the high-energy particles constantly bombarding Earth from space, are blocked by the overlying rock. Most other forms of background radiation are absorbed or scattered long before they reach the detector. The rock filters out nearly everything except neutrinos, which of course pass through the rock as easily as they pass through everything else. Deep underground, the detector sits in relative silence, shielded from the chaos of the surface, waiting in the dark for the faint signal of a neutrino interaction. And the detectors themselves are extraordinary. These are not small laboratory instruments sitting on a workbench. They are enormous structures, among the most ambitious scientific instruments humanity has ever constructed. Cavernous underground chambers filled with thousands of tons of ultra-pure material, watched over by thousands of exquisitely sensitive light detectors, all connected to electronics capable of recording events that last mere billionths of a second. All of this engineering, all of this effort, for one purpose: to catch the uncatchable. One of the most famous neutrino detectors in the world sits inside a mountain in Japan, roughly 1,000 meters below the surface. It is called Super Kamiokande. The detector is a cylindrical stainless steel tank, about 40 meters tall and 40 meters in diameter, filled with 50,000 metric tons of ultra-pure water. The water is so pure that it has been filtered and deionized to remove every conceivable contaminant. Normal tap water contains trace minerals, dissolved gases, and microscopic particles. All of these must be stripped away because even the tiniest impurity could scatter light inside the tank and produce false signals that would overwhelm the genuine neutrino events. Lining the inner walls of this enormous tank are roughly 11,200 light sensors called photomultiplier tubes. Each one is about 50 centimeters in diameter, roughly the size of a beach ball, with a smooth glass face designed to detect individual photons, single particles of light. These sensors are so sensitive that they can register the arrival of one photon in a completely darkened chamber. And the chamber is dark. 50,000 tons of water, 1 kilometer underground, sealed inside a steel tank, surrounded by rock on all sides. No sunlight penetrates, no artificial light enters. The darkness is total, absolute, unbroken. And in that absolute darkness, 11,000 glass eyes wait with infinite patience for the faintest possible flash. Here is what they are waiting for. When a neutrino, on extraordinarily rare occasions, interacts with a nucleus or an electron in the water through the weak force, the interaction can knock a charged particle loose. Typically this is an electron. The liberated electron is blasted forward at tremendous speed, so fast that it briefly exceeds the speed of light in water. Now, nothing can travel faster than the speed of light in a vacuum. That remains an absolute cosmic limit. But light travels more slowly in water than in a vacuum, because photons interact with the water molecules, effectively slowing their progress. An energetic electron does not interact the same way, and can temporarily outpace the light traveling through the same medium. When this happens, the electron produces a cone of faint bluish light, similar in principle to the sonic boom produced by a jet that breaks the sound barrier. Instead of a shock wave of compressed air, you get a shock wave of light. Physicists call this glow Cherenkov radiation. The Cherenkov light spreads outward in a cone from the speeding electron and strikes the photomultiplier tubes lining the walls of the tank. By recording precisely which tubes detected light and at exactly what time, measured down to billionths of a second, physicists can reconstruct the direction and energy of the original neutrino. They can determine where it came from, how much energy it carried, and what type of interaction it produced. All of this from a faint cone of bluish light in a dark underground tank filled with water. Super Kamiokande detects roughly 15 solar neutrino interactions per day. 15. Out of the trillions upon trillions of neutrinos streaming through its 50,000 tons of water every single second, roughly 15 per day actually interact. The rest pass through without leaving even the faintest trace. Each detection is precious. Each one is a tiny window into the heart of the sun or the depths of the cosmos, purchased at the cost of waiting through billions upon billions of silent misses. But Super Kamiokande is not the only approach. At the South Pole, buried deep within the Antarctic ice sheet, sits another neutrino detector of breathtaking ambition. It is called IceCube, and it is the largest neutrino detector ever built. IceCube does not use a tank. It uses the Antarctic ice itself as its detection medium. A full cubic kilometer of ice, stretching from roughly 1.5 kilometers to 2.5 kilometers below the frozen surface. 86 cables of light sensors were lowered into holes drilled deep into the ice. Each cable carries 60 sensors for a total of more than 5,000 light detectors distributed across 1 billion tons of glacial ice. When a neutrino interacts with a molecule in the ice, the resulting charged particle produces Cherenkov light just as it would in water, and the sensors record the flash. IceCube is designed primarily to catch high-energy neutrinos from cosmic sources. Exploding stars, jets from supermassive black holes at the centers of distant galaxies, colliding neutron stars, and other violent astrophysical events. These neutrinos carry far more energy than solar neutrinos, which means their interaction cross-sections are larger, and they produce more dramatic signals when they do interact. IceCube has already detected neutrinos originating from outside our galaxy, particles that traveled millions or even billions of light years across the universe, passing through countless stars and planets and galaxies along the way, only to finally interact with a single molecule of Antarctic ice and leave behind a flash of blue light for human instruments to record. Now, let me tell you what these rare catches have revealed, because the scientific payoff of neutrino detection has been extraordinary. Neutrinos have given us knowledge that no other form of observation could provide. The first and perhaps most fundamental revelation was confirming that the sun is powered by nuclear fusion. By the middle of the 20th century, physicists were confident that the sun generates its energy by fusing hydrogen into helium deep in its core. The theoretical framework was solid, the equations balanced, but there was no direct proof. All the light and heat we receive from the sun originates at its surface, not its core. Photons generated in the core take roughly 100,000 years to work their way outward through the dense solar material, bouncing off atoms, being absorbed and re-emitted millions of times, gradually migrating toward the surface. By the time a photon escapes into space, it carries no direct information about the conditions at the center where it was originally born. Looking at sunlight tells you about the surface of the sun. It does not tell you what is happening at the core, but neutrinos pass straight out. A neutrino produced in a fusion reaction at the sun's center escapes the star almost immediately. It does not bounce. It does not get absorbed and re-emitted. It flies out of the core, through the entire body of the sun, across 93 million miles of space, and through your body, all in about 8 minutes and 20 seconds. Neutrinos from the sun are direct messengers from the fusion furnace at its heart. They carry information about conditions at the core as those conditions existed just minutes ago, not 100,000 years ago. In the late 1960s, an American physicist named Raymond Davis built a neutrino detector deep inside the Homestake gold mine in South Dakota, roughly 1.5 kilometers underground. His detector used 100,000 gallons of perchloroethylene, a common industrial cleaning fluid. When a neutrino interacted with a chlorine atom in the fluid through the weak force, it could transform the chlorine into a radioactive form of argon. Davis would then painstakingly extract the argon atoms from the massive tank, count them, and calculate how many neutrino interactions had occurred over a period of weeks. The experiment was extraordinarily difficult. He was searching for roughly 15 to 20 argon atoms produced among hundreds of thousands of gallons of fluid over the course of a month. Davis found the neutrinos. He detected them, confirming that nuclear fusion was indeed occurring in the sun's core. Direct evidence carried by particles that had been inside the solar furnace just minutes earlier. But there was a problem that would haunt physics for 3 decades. He detected only about 1/3 as many neutrinos as the theoretical models of the sun predicted. The sun appeared to be producing far fewer neutrinos than it should. This discrepancy became known as the solar neutrino problem, and it remained one of the most stubborn puzzles in all of physics for over 30 years. Was the model of the sun wrong? Were the fusion rates different from what physicists had calculated? Was something wrong with the detector? The answer, it turned out, was none of the above. The answer was that neutrinos themselves were doing something no one expected. Neutrinos come in 3 distinct types, which physicists call flavors. There is the electron neutrino, the muon neutrino, and the tau neutrino. Each type is associated with a corresponding charged particle. The electron neutrino is paired with the electron. The muon neutrino is paired with the muon, a heavier cousin of the electron. The tau neutrino is paired with the tau, an even heavier cousin. The fusion reactions inside the sun produce only electron neutrinos, and Davis's detector was sensitive only to electron neutrinos. Everything seemed straightforward. But in 1998, physicists working at Super Kamiokande made a discovery that changed particle physics forever. They found that neutrinos oscillate. As a neutrino travels through space, it does not remain as one flavor. It cycles between all 3 flavors in a quantum mechanical process called neutrino oscillation. An electron neutrino born in the sun's core might arrive at Earth as a muon neutrino or a tau neutrino. It changes identity during the journey, shifting between the 3 types at a rate governed by quantum mechanics and the tiny differences in mass between the 3 flavors. This explained the solar neutrino problem perfectly. The sun was producing exactly the right number of electron neutrinos. The models were correct all along, but by the time those neutrinos reached Earth, roughly 2/3 of them had oscillated into muon and tau neutrinos. Davis's detector could not see those other flavors. It was counting only the electron neutrinos that happened to arrive still wearing their original disguise. The missing neutrinos were never missing. They had simply changed form during the trip. This discovery also proved something else of profound importance. For neutrino oscillation to occur, the three flavors must have slightly different masses. If all three were massless, oscillation would be mathematically impossible. The physics is strict on this point. Oscillation requires mass differences. So the discovery of neutrino oscillation proved that neutrinos have mass. This was a landmark result because the standard model of particle physics, the theoretical framework that describes all known fundamental particles and their interactions, originally predicted that neutrinos should be completely massless. The discovery that they possess mass, even an incredibly tiny mass, was the first confirmed evidence that the standard model is incomplete. There is physics beyond it. Something deeper is happening that we do not yet fully understand. The physicist who led the Super Kamiokande team, Takaaki Kajita, shared the Nobel Prize in Physics in 2015 with Arthur MacDonald of the Sudbury Neutrino Observatory in Canada. MacDonald's detector used heavy water and was able to detect all three neutrino flavors simultaneously, providing definitive confirmation that the total number of neutrinos arriving from the Sun match predictions perfectly. Only the mixture of flavors had changed during transit. The Sun's physics was right. The neutrino's physics was stranger than anyone had imagined. Then there was supernova 1987A. On February 23rd, 1987, a massive star exploded in the Large Magellanic Cloud, a small galaxy orbiting the Milky Way roughly 168,000 light-years from Earth. It was the closest supernova visible in nearly 4 centuries. But before any telescope on Earth registered the light from the explosion, neutrino detectors caught the signal first. About 3 hours before the first visible light arrived, detectors in Japan and the United States simultaneously recorded a burst of roughly 24 neutrinos over a span of approximately 13 seconds. Think about what happened in those 13 seconds. Across the planet, buried deep underground, instruments that have been running quietly for years, watching and waiting in the dark, suddenly registered a cluster of events unlike anything they had seen before. At the Kamiokande detector in Japan, the predecessor to Super Kamiokande, 11 neutrino interactions appeared within 13 seconds. Normally, the detector might see a handful of events per day from all sources combined. To see 11 in 13 seconds was unmistakable. Something extraordinary had happened somewhere in the universe, and the neutrinos had arrived to tell us about it before light could. 24. Out of the roughly 10 to the 58th power neutrinos the supernova released in total, 24 happened to interact in our detectors. To appreciate that number, consider that the dying star radiated approximately 10 to the 58 neutrinos in a burst lasting roughly 10 seconds. That is more neutrinos in 10 seconds than the Sun will produce in its entire 10 billion year lifetime. The energy carried by that neutrino pulse was staggering, roughly 3 times 10 to the 46 joules, which is several hundred times more energy than the Sun will radiate across all the billions of years of its existence. And all of that energy, 99% of the total energy of the supernova explosion, was carried not by the spectacular visible blast that astronomers photographed, but by neutrinos that passed invisibly through everything in their path. The brilliant flash of light, the expanding shell of debris, the shock wave that could destroy entire solar systems, all of that represented merely the remaining 1%. The real explosion was invisible. It was written in neutrinos, and yet those 24 precious detections confirmed, in a single stroke, decades of theoretical work about how massive stars die. They confirmed that the core of a dying star collapses, reaches nuclear density, and rebounds, driving a catastrophic shockwave outward through the star. They confirmed the energy budget, the timescale, and the basic mechanism of core collapse supernovae. 30 years of theoretical astrophysics, validated by 24 particles caught in underground tanks on the other side of the universe from where the star died. Those neutrinos arrived hours before the light because neutrinos escape the collapsing star immediately. Light, by contrast, must fight its way outward through the expanding stellar material, delayed by interactions with a dense, turbulent plasma. The neutrinos flew straight through the dying star as easily as they fly through the Earth. They carried news of the explosion directly from the heart of the catastrophe, without delay, without distortion, without anything along the way altering their message. The death cry of a star, spoken in the language of the weak force, crossed 168,000 light-years of space, and was heard on Earth 3 hours before anyone could see it. And this brings us to the deepest insight of our journey tonight. The very property that makes neutrinos so difficult to detect, their near total refusal to interact with matter, is precisely what makes them the most extraordinary messengers in the universe. Light can be blocked. Stars are opaque to their own radiation. Dust clouds absorb visible and infrared light. Dense plasmas scatter radio waves. The cores of stars, the interiors of supernovae, the hearts of galaxies shrouded in gas and debris, all of these places are hidden from us when we try to observe them with light. Electromagnetic radiation, for all the information it has given us about the cosmos, has a fundamental limitation. It interacts with matter too readily. It gets absorbed, scattered, deflected, and blocked. There are places in the universe that light simply cannot escape. Regions so dense, so violent, so shrouded, that no photon emerges to tell us what is happening inside. But neutrinos walk straight out. They do not care about the density of the material surrounding them. They do not care about magnetic fields or electric fields or the crushing pressure of a collapsing stellar core. They pass through it all as easily as they pass through the air in front of your face. A neutrino generated at the center of a collapsing star, surrounded by matter so dense it would crush atoms into a sea of neutrons, flies outward through that incomprehensible density and emerges on the other side carrying its information intact. This means neutrinos give us a window into places we could never otherwise see. They let us look directly inside the sun's core. They let us witness the precise moment a massive star dies. They let us probe the environments near supermassive black holes and the engines driving the most violent explosions in the cosmos. They carry information from the most extreme and hidden environments in the universe, places where no light escapes, places where conditions are so violent that any electromagnetic signal would be destroyed before it traveled a fraction of a centimeter. Right now, at this very moment, neutrinos from the Big Bang itself are passing through your body. These primordial neutrinos, called the cosmic neutrino background, were released when the universe was roughly 1 second old. They have been traveling through space for 13.8 billion years. They carry information about the conditions of the universe at an age far earlier than any photon can reach. The oldest light we can observe, the cosmic microwave background radiation, dates from roughly 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and light to travel freely. But neutrinos decoupled much earlier, when the universe was a mere second old. If we could detect these ancient neutrinos, they would open a window onto the infant universe at an age 380,000 times earlier than the oldest light we can see. They would carry information from a moment so close to the beginning of everything that the universe had not yet formed atoms, had not yet become transparent to light, had not yet cooled enough for the forces of nature to settle into the forms we recognize today. But detecting them may be the single hardest experimental challenge in all of physics. These primordial neutrinos have been cooling for 13.8 billion years as the universe expanded. Their energies have redshifted to almost nothing, far below the energies of solar neutrinos, far below anything current detectors can register. And as we learned earlier, a neutrino's interaction cross-section depends on its energy. Lower energy means a smaller cross-section. These cosmic relic neutrinos have energies so low that their cross-sections are staggeringly smaller, even than the already minuscule cross-sections of solar neutrinos. They are the faintest whisper of the faintest force, stretched thin by the expansion of the universe itself. Catching one would require a detector of extraordinary sensitivity, capable of registering an interaction so subtle it borders on the threshold of what measurement can mean. Physicists are designing experiments to attempt exactly this, including a project called Ptolemy that aims to detect relic neutrinos through an incredibly precise measurement of the energy spectrum of beta decay. If it succeeds, it will be one of the greatest experimental achievements in the history of science, a direct observation of particles that last interacted with anything when the universe was 1 second old. And so we arrive at the deepest irony in all of particle physics. The particle that barely notices the Earth. The particle that could fly through a light year of solid metal without stopping. The particle that ignores electromagnetism, shrugs off the strong force, and answers only to the weakest, shortest-ranged interaction in all of nature. This particle, precisely because it refuses to engage with almost everything, becomes the ultimate cosmic messenger. It sees what light cannot see. It escapes from places light can never escape. It carries pristine, undistorted information across billions of light years because nothing along the way interacts with it enough to corrupt the message. Every second, trillions of these messengers stream through your body. They arrive from the sun, from distant supernovae, from the cores of galaxies billions of light years away, from the first second of the universe itself. They carry information about the most extreme and hidden environments in existence. They pass through you without a trace, without resistance, without the slightest awareness from any cell in your body. You are bathed in information from the heart of the cosmos at every moment of your life, and you never feel a thing. The Earth sits in this endless river of neutrinos and barely slows it down. 8,000 miles of rock and iron and molten metal, and the stream passes through almost perfectly intact. The planet that holds everything you have ever known, every mountain and ocean, every city and forest, every person you have ever loved, is nearly invisible to these particles. They fly through it all, through every layer of stone and magma and compressed iron at the core, and emerge from the other side still carrying their secrets from the farthest corners of the universe. That is what it means that neutrinos barely notice the Earth. It is not a flaw. It is not a limitation. It is a revelation about the nature of reality itself. Solidity is not absolute. The impenetrability of matter is not universal. The tangible, resistant, solid world we build our lives upon is a product of one specific force, electromagnetism, and any particle that does not speak, that language moves through our world as though it were made of almost nothing. The neutrino shows us that reality has layers. The version we experience, the world of surfaces and resistance and weight, is one layer, written in the language of the electric charge. But beneath it lies a deeper emptiness, a universe of vast atomic voids and scattered nuclear specks, visible only to a particle stripped of every interaction except the weakest whisper of the weak force. Both versions are real, both are true, and the neutrino, the ghost particle, the little neutral one, lives in the version where planets are transparent, stars are barely obstacles, and the entire material universe is almost perfectly empty. We have built cathedrals of water and ice deep underground, lined them with thousands of glass eyes, and waited in the dark for years to catch a single flash from a single interaction. We have turned almost never into sometimes, and what we have found has rewritten our understanding of the sun, of dying stars, of the fundamental particles that make up existence itself. Trillions of neutrinos are passing through you right now, through the screen you are watching, through the walls around you, through the floor, the bedrock, the mantle, the iron core of the planet, and out the other side into the darkness of space. They have been doing this since before you were born. They will continue long after you are gone. They are the universe's quietest travelers, carrying its deepest secrets, crossing all of creation without stopping, because to them, creation itself is almost perfectly, beautifully transparent. Sleep well tonight. The neutrinos will keep passing through,